Like I was saying last time, linear search. This is an exceptionally important algorithm. Everything we've written so far has been an algorithm, but there are some algorithms that are so foundational and noteworthy. I would say linear search is your first big algorithm that we care about. It's a general purpose algorithm. You're going to be using variations of this a lot. This whole course, we use a lot of different variations of this algorithm to solve all our problems. Starbucks assignment is this. The assignment 2 is basically this. Assignment 3 is kind of like this. Assignment 4 is a lot of this. There's a lot of linear searches that we're doing. And that's not because I'm like ham-fisting linear searches into it. It's because they just come up a lot. And what's interesting about a linear search is you all know how to search for things. If I gave you a stack of papers and told you look for something in it, you'd know how to do it. You all know what to do. But you've probably not thought about it too much in terms of the underlying units of work. And in spite of that, a lot of you, when you're going to explain this to yourself or others, you're going to get it wrong because you're going to forget something that you do definitely know, but you're going to somehow forget it. It's weird. You'll see. And it really comes down to being how we have to write the code to say what we mean. So this algorithm is going to come up a lot. It's core, it's foundational, it's big, it's important. But you all know what it is. You all know how to do it. And the basic idea is this. Well, here, let's see where I go. You know what? Yeah, let's actually do this. Write this function. Character is in. I'm going to give you a few minutes to do this because this is a big one. What I want you to do is write a function that will take a character and a string, and you tell me if that character is in that string. You got to use a for loop. You could use a while loop if you want, but I recommend using a for loop. And just have this function return true if you found it and false otherwise. So, okay, write a function character is in that searches for a specific character needle within a string haystack. If it exists, return true and false otherwise. When you've finished, be sure to test it with the following assertions. I'm going to give you a few minutes to do this one because I think it's important that you try it out. If you're stuck, remember you can talk to each other. It doesn't have to be quiet in here. Raise your hand if you're done. Okay, I'm not rushing you. Just checking. So yeah, raise your hand if you're done. Raise your hand if you thought you were done, but the tests are failing. Okay. I'll give you a few more minutes. Okay, raise your hand and keep it up if you're done and it works. Really high. Cool. Raise your hand if, well, you finished it, but it failed. Really high. Really high, high, high. I want to see. Now, keep your hands up, keep your hands up, keep your hands up, keep your hands up. Keep them up. Up, 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 up. Did it fail? Keep your hand up high. Come on, come on, come on. Keep your hand up. You can only put your hand down. Keep your hand up if it passed all the tests but the last one. Okay, cool. Keep your, now, okay, you can put your hands down. You're good. So the last one got you, and I knew it. I knew it. And for the other ones of you that didn't have your hand up for anyone, you either didn't finish it, which is fine, or you're lying, which is, don't lie. And the reason I'm saying that is because this is if that's what happened, if all those tests passed except the last one, you made a mistake that I would say more than half of the students will make. They're going to make a mistake. More than half the students are going to make this foolish mistake. And I know you know, pardon me while I figure out how to word this the best way. If you've been following along with everything in the course so far, if everything's made more or less good sense, you feel pretty good about everything, but you got this one wrong, I guarantee it that when I show you the mistake, you're going to go, obviously, obviously. Meaning you're smart enough to see it, right? But you made a mistake that is so common. I would say 9 times out of 10, if you've made a mistake on this, this is the mistake it's going to be. And I think more than half of the students at this stage will be wrong because of this little mistake. So what I mean by this is, don't feel bad if you made this mistake. I deliberately designed this to be like a bit of a gotcha. So you're normal. So if all the tests pass, great. If all the tests pass, but the last one, I gotcha. So let me put it this way. If I have a stack of papers, right, and you show up to my office and you ask the question, hey, is my name on any of those papers? This giant stack, okay? First thing I'm going to tell you is, I don't know. You tell me. So what are you going to do? You're going to start looking through that stack of papers. That stack of papers is not ordered in any way. It's not like they're in alphabetical order or anything. They're just there. So you take the first paper off, okay? Obviously, you're going to need a loop. Look at each piece of paper or something, right? You take the first piece of paper off. Now, pause. Raise your hand again if all the tests pass but the last one. Really high. Wait, what happened? Apparently, everyone fixed it in the meantime. Well, that's wonderful. You take that first paper off. And your name's not on. No, let's say you take the first paper off and it's your name. Can you conclude if a piece of paper in that pile had your name on it at this stage? If you're looking at a piece of paper from that pile with your name on it. This isn't a trick. I realize it sounds like a trick question because it's so goddamn obvious. Hey, is my name on any paper in here? Well, let's take the first paper. Oh my God, my name's on it. Was your name on a piece of paper in that pile? Of course it was. Let's say it's not. Can you conclude that it is, oh, well, then you must not be in there? Yeah. Of course not. You've got a whole goddamn pile of paper to look at. You can conclude that you found the thing you're looking for the moment you find it. But you can only conclude that the thing you're looking for isn't there after you've looked at everything. Because if you've gone through a pile, there's a billion things in this pile, and you've looked at, and there's no order to them at all, and you've looked at 999,999,999 of them. There's one piece of paper left. And you haven't seen your name on any of those papers. Could your name be on that last piece of paper? Of course. Of course it could. It's just as likely to be on that one than any other one. No, let me do it another way. I've got a list. If I look at that first element of the list, at any given time, I only know what the thing I'm looking at is. So I say, go look at that first element. And I go, okay, well, let's look at that first element. It is an A. Is A what I'm looking for? If it is, great, I'm done. If it's not, what do I do? Look at the next element. It's a Y. Is that what you're looking for? If it is, great. If not, well, you got to keep going because you don't know what's to come. You can conclude that the thing you're looking for exists the instant you find it. But you cannot conclude anything about whether it doesn't exist until you've looked at literally everything. So hopefully this is clear. Let's translate this to the code. For C in haystack, I'm using C as the variable here because it's like a character. So for each character in the haystack, right? Haystack is some string. And C is going to be an individual letter, and I'm looking for an individual letter, needle. So I say, hey, is C the needle? Is the current character I'm looking at the thing I'm looking for? If it is, return true. If the thing I'm currently looking at is the thing I'm looking for, I'm done. I found it. Otherwise, what do? I keep looking. I can only conclude. I can only return false after the loop is done. If I've looked at every single thing in that pile of paper and never said I found it, and I get to the end, there's nothing left, and I never found the thing I'm looking for, that's when I can conclude it ain't there. Only then, only when I get to the end of the loop. So that's the simplest linear search. If I hit run, all the tests pass. Good. Oh, but I don't know what that is. Perfect. But if you made a mistake, I'm willing to bet, and if your mistake was shown by all the tests passed but the last one, you did this. Or some variation of this. Well, if that false, right? Is C, is A in, well, that doesn't make any sense. Let's not worry about that because that's an edge case anyways. There we go. Assertion error. Why? Well, let's ignore this one too. Is A in hello? Well, no. Is H in hello? Yeah. Is O in hello? Apparently not. But it is, obviously. And it's because, well, what does the code say? The first two were correct by dumb luck. We got lucky. I say, look for A in hello. So I say, give me the first letter in haystack. That's an H. And I ask, hey, is H equivalent to A? False. So what do? Well, I don't return true. I return false. Oh, okay, cool. But all I ever checked was the first letter. Let's try it again with H. So I'm looking for H in haystack, for C in haystack. So that's an H. Does H equal H? Yeah. Return true. Great. I only looked at the first letter, but I found it, so whatever. So now let's look for O. Or to make it even more obvious, let's look for E. So, for C in haystack, well, C is going to start at H. Is H equal to E? No. So return false, function's done. It's false. Yeah, that's not what we want. We cannot conclude this if-else will only apply. This loop here can actually, the way this is written, because of the returns, and a return immediately stops the execution of the function, because of the returns, although there's a loop there, that loop ain't looping anything. It can't. All it will ever do is look at the first letter. That's it. It can never go again, because either it returns true or false, and that stops the function. Whoops. That's the way to do it. What does the code say? Well, let's look at the last assert there. E and hello. So C starts at H. Is H equal to E? False. Do I return true? No. All right, I just go back to the loop. C becomes the next letter, E. Is E equal to E? Yes. Return true. We're done. It's critically important you understand linear search. So if something has you scratching your head, ask now before I move on, because we're going to be moving assuming this makes perfect sense. Yes?
Is the variable C defined in the loop?
Yes. Yeah. Does that answer your question?
Yeah, kind of.
Okay. Do you have a follow-up question?
I just wasn't sure if we needed to define, show how it equals each character in.
So what we could do, just to convince ourselves, well, let's get rid of the asserts. Notice, though, that we only had one letter printed out. Well, because the function finished. Why? Well, C became the letter H. Okay, you know what? The fact that I'm using C can be confusing. So let's call this char. There. That might be a little better. Char becomes the letter H. And then I say, print out char. That's H. Hey, does char equal needle? True. Return true. Okay, great. We're done. The loop isn't going to run anymore. It doesn't need to. The moment I find it, I'm done. I don't need to keep looking. I could ask a different version of the problem where it's like, count the letters of H, the number of times a certain letter exists. Well, that's different. I would keep looping then because I need to count how many there are. But that's a different problem. A very, very similar problem. It would be like the algorithm would be a variation of a linear search. But the most basic form of a linear search is, hey, is it there or not? You had a question?
If you want to find the same letter, but it's repeated in the string, how would you do that?
Okay.
Or if you wanted to print it anyway. Because the way it's set up right now, I think it stops. So if you want to print E in a word that has two E's, it stops on the first one.
Yes. So all you would have to do is, I mean, there's a couple of ways we could do it, to be very clear. We could do it literally an infinite number of ways. But what we could do is, we could say, like, is found equals false. And then if we find it, we can say is found equals true. And then down here, we return is found. There. Oh, what did I do wrong? Is. There. So now it will repeat all of them, no matter what. So this is a variation of the problem where I don't end early, which is fine. It's just a slight variation of the algorithm. One stops the moment I find it. The other one just goes, oh, I found it, great, and then it carries on. Did that answer your question? Yeah? At least close enough? Okay. We'll go to this version again, though, where it stops early. If I'm looking for y, which doesn't exist, well, this is showing you because it's printing out each letter, that means I'm putting my finger on each letter and checking. We get to the end, we never found it, we never found it. If I put in an L, if I look for an L, we will see HEL. Because look at H, that's not it, do it again. Look at E, that's not it, look at it again. Oh, we see an L, that's it, we're done. But why didn't it go to the next L? Well, because as soon as we found one, we're done. If you wanted to keep looking at all the L's, well, you could do some version of what I just showed you based on his question of, well, just keep going through the whole thing still. And sometimes you might need to. Obviously, we could say, look, in terms of saving resources, if our problem lends itself to a solution where you can stop early, well, that's good. You're doing less work. Less work means less energy. And where we live, that means less coal being burned. Yay. But if the version of the problem that you're solving is, well, we got to look at everything anyways just because of X, Y, Z, well, it is what it is. You got to keep looking. So it's always important to be a little cognizant of the amount of work your code is doing. So let me ask you this, though. On that idea, if I have a list, pay attention. This is a very important idea. And this is the first time, I would say, the first time I'm going to pose a question to you that gives you a glimpse into a lot of what computer science is actually about. Computer science is not about writing code. The question I'm about to ask you gives you a glimpse towards what we're actually really caring about. So listen, if I have a list of 1 billion pieces of paper, okay, 1 billion. Maybe it's 1 trillion. Maybe it's a zillion. I don't know. It's a big number. Some arbitrarily large number. Okay? And you're going to start on the first piece of paper, and you're going to check for your name. All right? So you grab it, and you look. If you find it, great. If you don't, keep going. What's the best case scenario? Yeah, you find it on the first try. So best case scenario, how many things do you have to look at? 1, yeah. That's pretty good. But what about the worst case scenario? Yeah, the worst case scenario is it's on the last one, or hell, even it's not there at all. Right? You still got to look at everything. So if I've got, let me put it this way. If I have this pile of paper that's 10 big, your best case scenario is you found it in 1. If you had a pile of paper that's 100, your best case scenario is still 1. If it's 1 million, best case scenario is still 1. A bajillion, still 1. But worst case scenario is a little different. Worst case scenario is if you have a pile of 10, how many things do you have to look at? Remember, worst case scenario, it's not there, you got to look at it all, so worst case scenario is 10. If I double it, how much more work do I have to do? Worst case scenario. Double. So it's 10. Let's say it's 100. How much more work do I got to do? 10 times, well, 5, whatever, right? If it's 100 units if there's 100 pieces of paper, I got to look at all 100. If it's 1 million, I got to look at all 1 million. Let's say it's n. There are n sheets of paper, where n is some arbitrarily large number. Worst case scenario is I have to look at all n things. I have to put my finger on each piece of paper, all n of them, and I get to the end and I conclude it's not there. So worst case scenario, it's n. If I double n, so it's 2n, how much more work do I do? Twice as much. Yeah. This is an example of what we would call, a linear time algorithm. Now I have to be careful that I'm communicating to you what I mean when I say that. You might think, and yes, this is all related, you might think, okay, I've got n things in there, and if I have to look at all of them, that's like n units of work, right? A total of n total units of work. Assuming each thing takes 1 unit of work, and I have to do n things, that's 1 times n, well, that's n, right? So that might, oh, linear, okay, it's not like n squared. There's no, like if I were to draw this on as a line, the amount of work we do grows linearly. What I mean is, it grows like a straight line. We've been drawing these since you've been about this big. Straight lines. They're crazy. When we say it's linear, it's not so much about how much work is being done on any particular instance. It's more about how much more work needs to get done as I make that n bigger. If I double the size of n, I have to do twice as much work. If I make it a factor of 10, I have to do 10 times more work. The amount of work grows linearly. You double, you double. This would be as opposed to like non-linearly, like quadratically, where if you double the amount of work, you have to do, or sorry, if you double the size of n, you have to do 4 times as much work. Things might grow like this, where as it gets bigger and bigger and bigger, it's not twice as much work. You're doing a lot more work. Some problems, we're kind of stuck with algorithms that kind of look like that. A linear search is great and all, right? Want to hear something wild, though? There are search algorithms that are a little different. So if I were to tell you, I've got an algorithm that is worst case scenario will take n units of work. If I have an input size of n, this algorithm will take worst case scenario n units of work. That's pretty good. But if I were to tell you I got one that's better, it just takes less amount of work, you're going to say, well, awesome. I want an algorithm that takes less, does less work. That's way better. So what is it? Well, let me put it this way. This algorithm is, so with the linear one, if I double the size of n, I have to do twice as much work. But there's another search that we're going to learn soon. That is, if you double the size of n, I have to do 1 more unit of work. Only 1. If you double it again, only 1 more unit of work. You double it again, only 1 more unit of work. And you want to know the best part? You all know this. You all know this algorithm. Whether you like it or not, you know it. We're going to talk about it a little bit later. Does anyone in here have a textbook? Like a physical textbook? One person. Hey, perfect. Here. I'm going to use you as an example. Do you mind being on camera?
Sure.
Perfect. Come stand right here. Let me see that textbook for a second. I'll give it back real quick. No, spoiler. No, come back. You're going to do this. Okay, here. Everyone watch what he's going to do. And all of you would do the same thing unless you're psychotic. Turn to page 600. Watch what he does. Did that take 600 units of work? No. How come you didn't do this? Close the book. How come you didn't do this? Is that page 600? Is that page 600? Is that page 600? Is that one? How about that one? No. That's ridiculous. The point being, what do? Well, you go, okay, well, let's see. Let's go about halfway. I'm looking at page 368 and 369 this way, right? So if I'm looking for page 600, what side is it on? This side. Do I need to look at over here? No. I mean, I've eliminated like almost like 368 pages from my search. You can go sit back down. So that's what you would call like a variation of what we would call a binary search. And that is a search algorithm where you can find things a lot faster. But there's a big catch. The big catch is that the data that you have must be ordered in some way. You must be able to look at where you are and say, where should I keep looking? This way or this way? If I were to say, guess a number between 1 and 1,000, or 0 and 1,023. Who wants to, let's do a really quick example. I need a volunteer. You. You're going to pick, don't say it out loud. Whisper it to him so you can confirm we're not cheating. I don't want to hear it. I'm not looking. I'm going to use a calculator though because I'm okay, perfect. So, let's start like this. Is it 1? Is it 2? 3? 4? 5? 6? 7? 8? 9? 10? 11? 12? 13? 14? 15? 16? 17? 18? 19? 20? 21? How many guesses? I made 21 guesses. I'm not there. I got a long way to go. I mean, maybe I'll find it. I don't know. Of course. So how about this? I'm going to ask you, but you have to do something for me. You have to say higher or lower. So is it 512? Higher? 768? 640? 576? 608? 624? 616? Oh, you picked a good one. 620? 618? I said -8. I said 616.
Yeah, and I said higher.
And you said higher. And then I said 620. You said lower.
Yeah, you said 618, then I said lower.
618. Okay, yeah. So 617. Yeah.
Yeah.
Perfect. I forgot how to count. That was my fault, not your fault. So he picked the worst case scenario. I had 10 guesses there. That was 10. That's the worst case scenario. It's not possible for me to have guessed it in more. So you picked a good one. Nice. You could have just said 512 plus 1. But, the point is, I made a guess, and then I went halfway between the upper limit and the lower limit. Halfway. I kept narrowing it down. You all know this search because I know you all know how to turn to a page in a textbook. That's an algorithm where if I double the size, with a linear algorithm, I have to do twice as much work. With this algorithm, it's called logarithmic because it's dividing by 2 every time. Log base 2. We're going to be, if you double the input size, I only need to do 1 more unit of work. If I asked, so I said pick a number between 0 and 1,023. If I said 247, 0 and 2047, I would have got it in no more than 11 guesses. And if I keep doubling, I only have to add 1 more guess. Because think about it. If you don't believe me, let's say I said 0 and 511, right? That would have been 9 guesses. And then I'd tell you, well, with 1 more guess, I can get it between 0 and 10,023. And you'd say, like, well, why? Well, my first guess would be 512. And then you'd tell me, well, is it lower or higher than that? And then after you answer that, I'm just doing the search between 0 and 512. We'll get more to this later. I am jumping ahead. I think you're bright enough to be able to go with me on this. Any questions about linear search, though? All right, so linear search. So the underlying idea, generalizing beyond strings, we can do linear search on literally any linear collection. A stack of exams, a lineup of people, but it's important to note that we can confirm that a given element exists as soon as we find it, and if I'm looking for X in a sequence, I can confirm its existence as soon as I see it. For example, consider looking for X in the following sequence. They're question marks because I don't know what they are yet. I've got some unknown sequence. Until I look at them, I can't say what they are. If I'm looking at the beginning of the sequence and I see an X, hey, I'm done. But if not, I got to go again. I got to keep going. If I'm looking for Y and I see an X, can I confirm if Y is there? I can tell you X is there, but I can't tell you if Y is there yet. I got to keep looking. So why is this one broken? Well, this is a while loop version of what I did before, where it's if, else. Basically, this would only ever look at the first thing, 0th thing. Now here's a variation. And let's do this right now. I'll give you a few minutes to do this. I'm going to give you a variation of this problem. It's a linear search, but I don't want you to tell me, actually no, let's skip this because this is in the lab. We'll skip this. We'll do this in the lab. The variation would be, don't just tell me if it's there or not, tell me what index it's at. But this is actually an interesting problem because now we're kind of like mixing types. What I mean here is, originally I had a function that returned a Boolean, true or false. True if it's there, false otherwise. Now I've got a problem that needs to return an integer, a function that I want to return an integer. So it needs to return an integer of the index in which where something exists. But what do I return if it's not found? This is where, see, you'd be like, a Boolean? Well, now you've got a function that might return an integer or a Boolean, which Python would be like, okay, but most programming languages would be like, this is a terrible idea, don't do this. Because it is a terrible idea, don't mix types like that. So how do we deal with this situation? Well, in this particular situation, what we would do is we create what we call a sentinel value. That's a special word that just means a special value that has special meaning in this context. So here, I'm saying, if I find it, return the index. If I don't find it, return -1. Now, I know in Python there is a -1 index. Not really, but kind of. When I say return -1, that has special meaning in this context. If I say, tell me the index where something exists, and it gives me a -1, that's not really a valid index. There is no index -1. Again, I know in Python there kind of is, but it's not really, because it's index length -1, not really index -1. There is no index -1. So it's like if I asked you, what's the length of that side of the square? Oh, it's a -1 length. It doesn't really make sense, right? So it has special, like because that answer, -1, doesn't make sense in the context of the problem, it can give a special meaning. And for us, a -1 would mean it's not found. Because otherwise, what integer would I return? 7? Well, that could be where the thing is. 99, that could be where the thing is if I'm doing a linear search. So we need to return something that has a special value, a sentinel value. So here is some string trivia I'm going to blitz at you. In Python, you can make a strings with two versions of quotes. You can use double quotes or single quotes. Who knows what I prefer? Double. And the reason I prefer double is, one, that's what's common in most languages, so it's good to be consistent. But two, what's nice about double quotes is if I have the string, right, I can add single quotes to them. Where if I use single quotes, and I try to add single quotes to the string, it's going to be like, ugh. You can do it with what we call escape characters. where you could be like, this backslash means like, shut up, I know, just pretend it's just that letter. You can do it, but that's hacky. So, you know, double quotes is nice. You can concatenate strings with addition. You can repeat strings with multiplication. You can convert integers to strings, right? So type 1, type of the string version of 1 is a string. You know, we could do that. But it only works for things that are valid to be converted, because you can convert strings to integers only if you can. Like you can't convert you can't convert the letter A to an integer, except you totally can, but more on that later. Does anyone know what integer anyone know what number the letter A is?
140.
No, 97, obviously. Clearly, just come on. You'll see why later. So you can have an empty string. You can have a string where there's nothing in it. A, open quote, close quote. You might say, that's not a string. Yes, it is. It's an empty string. And I can ask Python, hey, what's the type of this? It's a string. What's its length? 0. But it is a string. It's a string of nothing, which is entirely different than nothing. None is its own thing. We have special characters, and there's a lot of special characters. And for example, if I say write a string, but I want you to have go on multiple lines, how do you do that? Well, we got a problem. If I say A equals, I want this. I want it to say hello and then world on a separate line. And I hit run, and Python's going to be like, that's not a thing. Well, don't worry. /n means, well, print A. There. That means go to a new line. Anyone want to guess what /t does? Tab. I showed you that one already. There's a bunch of them. Yeah, here's A. Lowercase a is 97, obviously. And it's because of something called an ASCII table, but we'll pick up here on Friday because this is where it gets kind of weird.